Okay, hello, welcome back. So, starting this video, we'll be opening a new chapter in advanced dynamics, and we will start looking at rigid bodies. So far, maybe I don't know. Let's keep it here. So far, we have only been looking at particles and system of particles. They are good. They are extremely generalizable, and essentially any system we are dealing with, anything from cars, toys, human body, everything, we are essentially built of tiny particles. So everything we have said so far actually is applicable. It's correct for any system, any mechanical system we can think of. However, when we're talking about an actual rigid body, we have practically infinite particles in that body. And with those infinite particles, there's also infinite number of constraints that essentially constraining the distance between any of these particles. So working at that scale is, well, not practical. And precisely because of those constraints that the particles, every two particles within a body, within a rigid body, remain fixed relative to each other, that form of constraint actually gives rise to certain properties in that system of particles we are dealing with. And most of the work that we see here is done by Euler, who came a bit after Newton. Newton did only particles, and it took someone at the size of Euler to figure out how to do with rigid bodies. So let's see. First of all, let me define rigid body. It is useful to have a definition. Rigid body. So a rigid body is a system of particles. Let me write it down. A system of particles where the distance between every two particle remains constant. So essentially particles don't move relative to each other. Yeah, that is rigid body. So when we talk about this kind of system, a rigid body, we first of all let's try to analyze the motion of a single rigid body in its simplest case. So when we have a rigid body moving around in 3D space, we need to first describe how it is, where is it located, how is it oriented. So what we can do is, let me draw a nice 3D space, XYZ, and I have this box. I want to show it a little tilted. My drawing didn't work. But anyways, this is a rigid body. What we can do is essentially attach a frame somewhere on the body. So fix a frame to the body. So this frame is usually called a body fixed frame. And what we can do now, instead of just talking about randomly how the object is oriented and located in a space, we can dedicate our focus to only this frame, this body fixed frame. And let me to let me see what wording I have here. To fully describe where the body is. The body is, and by where we mean complete information, where it is and how it is located. And that information also gives us information about every particle within the body. To do that, we need to know where the origin of frame is and how it is rotated. So to fully describe the body, we can just dedicate our attention to the frame itself. The good thing is that the translation of the origin of this body fixed frame is easy. The problem is the rotation. Rotation is not. And really it needed someone with the abilities of Euler to figure out how to describe rotation in 3D. All right, so that's what we are going to do for now. For this video and the next few ones, we are just trying to describe rotations in 3D. Now to do that, let's just focus on rotation without translation. I have again a frame, a nice and good frame, and I'm going to create another frame at the same origin, only rotated. So this one, let's call it IJK. Let me do this. And the big one, let me have, let's call it X, Y, and Z, big X, Y, and Z. And the unit vectors are I, J, and K. And we want to describe the rotation between these frames. So what can we do? The most basic form of describing this rotation is for you to tell me exactly where the big I is, where the big K is, and where the big J is relative to the other frame. So that's what I'm going to do. So this I, the vector I have it here. This vector is, I can write it as a summation of its component along the little ijk. So let me try a third color. And to do that, I can find the projection of this vector I on the three other green ones, the little ones. So I, and I'm going to write it in a matrix notation. So I is I dot I along the little I, and j dot I along the little j, and k dot I along the little k. And that is my I in the XYZ frame, the little one, the little XYZ. Similarly, I can write my J in the XYZ frame. A bit longer. This one is black. This one. So it is I dot J along I, and little I, J dot J along little j, and K dot J along little k, and finally my K, big K in XYZ is I dot big K, J dot big K, little k dot big K. And these are the information I need to fully know how these two frames are oriented relative to each other. So I did this in matrix notation because now you see a pattern emerging. What I can do is define something called R, rotation matrix. The textbook is using C to describe rotation matrix, letter C. I have only seen it in this book. Everywhere else, it's either R or A sometimes. Yeah, I'm going to use R because that makes more sense. It's rotation, so R. And I'm going to just put these three column vectors next to each other. So I dot big I dot big J, I dot big K, J dot I, J dot big J, J dot big K, K dot I, K dot J, K dot big K. And this is what we call a rotation matrix. And what does it do? It rotates the frame. And to see that, what you can do is take this rotation matrix R and multiply it by 1, 0, 0, which was my I in the big XYZ frame. So this is the definition of I in that frame. And if you do this, you'll notice what we get is the first one, so I in the XYZ frame. So essentially, well, in fact, let me write this too. If you have any vector R and you multiply by the rotation matrix, you get the vector component in the rotated frame. And I'm glad I have this. Let me come a bit closer with the video so you see. So this is my coordinate frame. And to see what is happening, you might have seen it before. I'm sure you have seen it. I hope it's not too small, but I don't know how I can make my video bigger without stopping video sharing. So this is my panel. Let me use a different color so it's more visible. So I have a frame and I have my vector, the black one. And what is happening is I'm rotating my frame, and now the component of the same vector that didn't move. So the scene, the vector in the frame are not changing. I'm only rotating my frame, and now I'm looking at the components of the same vector in the newly rotated frame. So that's why we say this is a frame being rotated. And this R is going from big XYZ to the little XYZ. So essentially the rotated frame. It is the rotation characterization that we were looking for. So a few things. One thing, any of these terms. So I dot k, we are dot producing, is that the right word? I don't know. Dot producting two unit vectors. And what do I have here? I dot k. I dot k, which one is which? Oh, this is a good one. And that dot product, remember what the dot product is: length of one times length of the other one times the cosine between them. So the lengths of these two vectors are 1. And what these elements of the rotation matrix are essentially the angle between the original and the rotated frame. And these are called directional cosines. Directional cosines. How do you write cosine? Not like that. Oops, I deleted too much. Cosine, I think like this, right? I don't know. Directional cosine. I'll leave it at cos. So essentially, you need to find the angle between all these pairs of vectors and construct your rotation matrix. Another thing to remember, I have this R, I don't know, IJ, so that the elements of the rotation matrix. So like R1, 1, 1, 2, 2, 3, something like that. The first one is which one is it? The first one is the rotated frame. So components of it is related to the rotated frame. And the second one that covers the columns are the original frame. For instance, I don't know, R3, 2 is a little k and big J. And immediately you can see here that if I have a frame rotated, I have two rotated frames, one rotated to the other one. I have one rotation matrix. The other way around, rotating the second vector, second frame back to the first frame, is actually the transpose of the matrix. So if you have R transpose, it is rotation the opposite way. So rotating this frame to the next one is the opposite of rotating the second one back to the first one. And also you can see if I have, oops, where is my frame? I have my frame, I rotate it. Let me make it bigger. I have a frame, I rotate it and rotate it back to the same position it was before. So two consecutive rotation essentially take you back to the same place you were, and the transformation between them is just identity. Whatever you were looking at before, you will end up looking at the end. So if you do this first, let me do it the other way. R transpose R. So you have a vector, you rotate your frame, look at the new components, and then rotate it back to the same place. You're looking at the same thing. So this transformation is actually identity, I, the identity matrix. And from here, you can quickly, and it goes both ways. So it is the same as R transpose. Doesn't matter which direction you rotate first and then cancel it out. And from here, you see that R inverse is actually R transpose. So if you want to cancel your effect, you can rotate the opposite direction. And this is very useful because we don't have to take the inverse anymore. We just deal with the transpose. And immediately from here, you can see that the determinant of R has to be 1. Well, it can be plus or minus 1, but in this case, it is 1. And it makes sense. If you are rotating, you're not changing any size or dimensions of your system. That's what determinant do. Determinant, if you have a vector multiplied by a matrix, the length of this vector is essentially multiplied by the determinant. Well, it's a little more complicated than that, but the area of any shape will be expanded by the determinant. That's better thing. And because during rotation, you don't change the shape of anything, that makes sense that the determinant is 1. What else I have here? So the last thing I have is something, it always confuses me. And I think just half of the population of the Earth go one way, the other half goes the other way. What is the definition of rotation matrix? Rotation matrix, as we define it here, rotation matrix, the way we defined it here, rotates the frame. It does not rotate a vector. A vector. To see what I mean, let's look at my frame again. This is the frame. Let me do it this way. And this is my vector. So what is happening is I'm rotating the frame looking at the same vector. I'm not rotating the frame, the vector in the same frame. In fact, rotation of the frame like this is kind of equivalent of rotating the vector the other way around with the same kind of rotation. So in that sense, rotation of a vector is this R transpose. So you have to rotate, if you want to rotate a vector and see how it looks like in the same frame, you have to multiply by R transpose. So all right, that is, I think, all I have here. Let me see. And we covered that. Yeah. So that is the definition of rotation matrix. And this is not this is the most complete and foolproof way to describe rotation, but it is not the only way, and maybe it's not the best way for the reason we'll see in the next video. So I will leave you with this, ponder on this, and make sure you don't mix up which one's which, rotating the frame or rotating the vector. I always do. And I'll see you in the next video.